For our first presenter, it's James Saslow, and he's from San Jose University, State University, and his presentation is going to be about the role of tilt in colloidal membranes. So, James, if you would like, you can take the floor.
So yes, I will be presenting the topic of the role of tilt in colloidal membranes. This is a project I worked on remotely with Thomas Powers at Brown University. So to just get into things, what are colloidal membranes? Well, colloidal membranes are what you see here on the bottom image. There are these disc shapes here. They are lipid monolayers with FD vial rods attached to them. They're usually formed in some solution like dextrin, and they're about 3 to 4 microns across. And these green little dots you see on here, these are the FD vial rods. They are a couple of fluorescently labeled ones that they did an experiment. But there's not just 2 or 3 of them attached to them. These are just a couple of the fluorescently labeled ones. In reality, there's a whole assembly of them, as you can see on the cartoon on the left-hand side, for a colloidal membrane model of a disc. And the geometry of these rods, they are about 880 nanometers in height, as you can see on the right-hand side image, and they're about 7 nanometers in width. But that's just the case for a disc-shaped colloidal membrane. It turns out that colloidal membranes come in many different shapes and sizes, and they all have their unique rod orientation on them. So this raises the question, do curvature of different colloidal membrane surfaces cause these vial rods to tilt away from the normal of the surface? Well, when we examine these 2 images here, we have rod alignment on a flat membrane, which is what we saw before. For the most part, these rods tend to align to the normal with the exception of the rods on the edges here. But when we examine the rod alignment on a curved membrane, we see that we have curvature on the membrane surface. And these white little dashes here, these are the vial rods, and they are tilting. They are tilting away from the normal of the surface. So this gives us motivation to ask the question, how does curvature influence the desire for these vial rods to tilt? And a little good hint that we have is that each colloidal membrane surface has a preferred rod tilt orientation such that the total energy is minimized. And you can think of this in terms of these colloidal membranes are lazy and they want to tilt such that they spend the least amount of energy possible. So before we can talk about spending the least amount of energy possible, we first have to propose a model for the energy. So our energy is made up of 3 components, a liquid crystal energy, a depletion energy, and a volume constraint. And I'll get into what all of those components mean. So for our liquid crystal energy on the bottom left, here we have an image of a liquid crystal pneumatic. And what happens with a liquid crystal is that there are more ways for rods to align than for them not to align. So because of this, entropy favors rod alignment. Next, we have our depletion force. And what we have in our dextrin solution, we have these polymers that are floating about, and occasionally they hit these rods and they bounce off of them, and this produces a osmotic pressure. And this osmotic pressure is what's responsible for giving these colloidal membranes the property to self-assemble, so it wants to make these rods pack together. And finally, we have a volume constraint. And what this volume constraint does, it just tells us that the occupied volume of the rods is conserved. This is something that we observe in experiment, and so we want some consistency between our experimental model and what we observe in experiment by incorporating in this volume constraint factor. So next we have a method. We need to implement a method for minimizing the energy. So now we have an energy, we want to minimize it to find the configuration of rods that tilt, spending the least amount of energy. So our procedure for doing this is using the calculus of variations. And so how we do this is step 1, we write down the energy, which is what I did on the previous slide. Step 2, we solve an Euler-Lagrange equation. And in solving this, we obtain a differential equation, which is what we see in step 3. And so this differential equation in step 3 down here, this is the differential equation for the case of a spherical membrane at fixed volume. And these are the results that we get for examining a spherical membrane. We get 2 results. And these images that you see here, these are the 2D cross sections of 3D spherical membranes. These blue little dashes on here, these are the viral rods. And so we obtain two solutions. We get beta equals 0, and beta is proportional to sine theta, where theta is the longitudinal angle that goes around the circle like this. And beta is the angle between the normal and the virus rod. So the normal would point out this way, or I should say a good example would be over here. So the normal points out this way, and the viral rod points out this way. So the angle between those two would be beta. And so we get two solutions, as I said. So it turns out that for a large radius, we get low curvature. And for low curvature, then these rods tend to align with the normal for this cutoff condition you see on the far right here. But after we exceed some curvature threshold, this means that when the radius gets small enough, we get a large enough amount of curvature to where we get a very interesting rod tilt orientation, and that is beta is proportional to sine theta. So rods tilt for high curvature. And here's a 3D representation of that. For the beta is equal to sine theta solution, we have a diagonal view, we have a side view, and again, these blue rods are the viral rods, and the black arrows are the normal vectors. So, in conclusion, high curvature leads to tilt. In the future and limitations of this project, we should consider shapes with edges. A sphere is a nice shape that doesn't really have that. We should look at other axisymmetric shapes like the undulate and the catenoid. We should examine shapes that have negative Gaussian curvature. So for the sphere, for example, it's strictly positive Gaussian curvature. And we should try solving for the shape and rod orientation simultaneously. Although it's a harder computation to do, it would be good in backing this model. I would like to acknowledge the Leadership Alliance, Brown University, Thomas Powers, my PI, San Jose State University, especially the physics department, for motivating me to do this research experience, and the NSF for funding this project. Thank you, and I'm open to any questions you may have.
Thank you, James. This was a very interesting presentation and certainly a very thorough research on colloidal membranes. Just wait for a few seconds until questions come in, and I'll just ask them as they come in. Okay, actually, I just had a question until they actually started coming in. Are there other methods for kind of minimizing the energy for colloidal membranes, or is this like kind of how usual research is being conducted?
Sure, yes.
The method that you use.
So there are different methods. There are various computational methods where I think another way that they do it is they, instead of making a generalized case, they physically plot rods with different rod lengths on some membrane, and they're able to solve for the rod orientation and the surface that they're on simultaneously. It's a lot harder to do by hand, and usually you need computational methods to do that.
I do have a very specific question, and maybe it's a stupid question, I don't know. Can you go back to the slides? Apologize for that. Can't remember the slide number, but I think it's a slide after the definition of colloidal membranes. The image on the left, is this like the actual? I mean, I know it's a representation of it, but this is how they look like on a microscopic scale, or?
Yes. So this model is actually, it's a pretty backed model. It's almost, I think it's exactly what they observe in experiment. So this is pretty much for the most part, a 100% solved problem. So this is just a cartoon representation of that, what they observe in experiment for a disc-shaped membrane.
Thanks again, James, for the presentation. It's very interesting about like your research in colloidal membranes. And I'm pretty sure like if you had more time, you would have had more research on that as well, exploring other methods and so on. So yeah, thanks again.
Thank you for having me.